This conference will now be recorded.
So I would like to welcome everyone to GeoAquaWatch webinars. I'm very happy today that you are joining, and this is a series of webinars that we present in GeoAquaWatch to describe our activities. We are happy to introduce Claudia Giardino. She's going to be presenting this webinar, and she's a research director at CNR in Italy. She has a degree in environmental engineering and PhD in remote sensing sciences, received from Milano, Italy. We are happy to have her as she's actually having a long experience that includes remote sensing, activities in inland and coastal water, and she's specifically working on retrieval of biophysical parameters from the Earth observation, including, of course, the calibration and validation of hyperspectral remote sensing. I would like very much to invite her to give the webinar, please, on an imaging spectroscopy for aquatic ecosystem research and application with Prisma, but she's going to explain all about it. Thank you. Claudia, please.
Thank you, Gada, for the nice introduction. Hi to everyone. Good morning, good afternoon. It's a pleasure to be here. Thanks to the GeoAquaWatch for having offered me this opportunity to present the activity we are doing here at CNR in Milano. As introduced by Gada, I will talk about activity mostly specifically focusing on hyperspectral remote sensing. So I now start to share my screen and the slides I've prepared. For doing that, I think I will also turn off my video to save the band, but I will turn on later on, and please. And I hope you will enjoy the webinar. Thanks again for joining to everyone. Okay, so I would simply ask to Gada if she could confirm, do you see the screen and the slide presentations as a
Yes,
slideshow?
excellent. Excellent, thank you.
Okay, thank you. So as I said, the title of this webinar is Imaging Spectroscopy for Aquatic Ecosystems, and I will present the research and application developed with Prisma, which is an hyperspectral satellite system developed by the Italian Space Agency. This works in cooperation with my colleague, the PrimeWater Consortium, as this part is also shared within this project, and also the wide community of people I have the opportunity to work on with hyperspectral data since many years ago. So the outline of the presentation is presented in this slide. As the webinar is based on Prisma, I will present the status of the mission and the main features of this hyperspectral sensor. And later on, I will show the exploitation of Prisma data in the specific field of aquatic research studies, and the work we are doing for the European project named PrimeWater, in which we established an Earth observation science virtual laboratory that I will introduce later on. I will end the webinar with some conclusions and ongoing activities. So the satellite was launched already in 2019. It was March of 22nd. The successful launch was performed actually on the 22nd of March. And in this table, you can see the main characteristics of the Prisma missions. So it has an orbital polar orbit with a relooking time of less than 7 days due to the capacity of the sensor to be tilted because the platform is moving. And so even if the nominal repeating cycle is of 29 days for the nadir viewing observation, thanks to this capability of tilting the sensor, we can increase the revisiting frequency of satellite acquisitions. This is, of course, one of the main improvement of such kind of technology, as we do know that hyperspectral remote sensing is a kind of technology which has a high data rate, so it consumes a lot of power to download to provide hyperspectral data at a reasonable, moderate to high spatial resolution data. But thanks to this technological improvement, the repeated cycle of 29 days can be improved. Those are other characteristics in terms of the sensor, which is on board of Prisma. Actually, Prisma also provide an hyperspectral data cube within the visible near-infrared bands and the shortwave infrared bands at a ground sampling distance of 30 meters. But it also carries on board a panchromatic camera, which acquires data co-registered with the hyperspectral data cube with an improved spatial resolution of 5 meters. Those tables also show some other characteristics in terms of the requirements that were established at the beginning of the missions. And in particular, the SWOT of the sensor is of 30 kilometers. The nominal size of the single imagery is actually a box of 30 by 30 kilometers, but Prisma can also acquire data along the orbits, so that actually stripes up to 1,800 kilometers can be acquired for any site of interest between the 70 plus minus 70 degree of latitude. Another characteristic of such kind of technology is given here. So in terms of signal to noise ratio, this is we are part of the aquatic community. Those are of course not optimized for observation of dark targets such as water bodies, but this is of course a limit of the technology, because it has to provide a high number of bands within a 30-meter spatial resolution. So those are the nominal signal to noise ratio from the visible to the shortwave infrared. In particular, in the visible to near infrared range, which is the one most used for aquatic application, those data we will see later on are comparable to those of the Sentinel-2 missions, which is actually rather well used also for aquatic applications. So those are some statistics kindly provided by our colleagues from the Italian Space Agency, which are updated to June of this year, in which you may see how the users who are using Prisma data are distributed across the countries. We do have, of course, a high percentage of users coming from Italy because it's Italian missions, but later on there is a pretty high interest also globally distributed. In particular, we do have a lot of colleagues from the States, from India, China, and also other European countries. Those are the statistics, again, with the people who are using Prisma data with respect to the category in which they are belonging. So we do have most of the users who are scientists. We still believe that hyperspectral data are still rather complex for being provided as services. So there is a lot of interest for scientists on this data. But still, we do have an increase with respect also to commercial institutional users, some small, medium enterprise, and also a community of 60% or freelance, which I assume are people not affiliated to any of the above categories. Also, with respect to the thematic areas in which Prisma data are used, this graph shows the statistics, still updated at June of this year, in which most of the applications are devoted to land, in particular to agriculture, which is a thematic field in which hyperspectral data has been demonstrated to provide a lot of advantages with respect to multispectral observation. We have, of course, then all the category of land in terms of also geology, for which the SWIR part is very relevant. But at certain moment, coastal areas water quality comes up. So as said, even if the mission has not been designed with requirements driven by aquatic application, still the data provide interesting data for aquatic applications. And also this comes from the Italian Space Agency, in which the collection of imagery data available so far as collected by Prisma are plotted on the globes. So again, most of the data are collected on land because the background missions in which Prisma systematically corrected are mostly focused on land. Then there is, of course, the acquisition which are performed on interest of users, which can be also distributed, not necessarily to land. And actually, we do see also acquisition, a lot of acquisition, of course, in coastal areas, but also in oceans, because actually the sensor can be tasked to acquire data in any part of the globe. So after having presented the mission, let's talk about the data Prisma offered. So this is a true color imagery from hyperspectral Prisma Data over the Venice Lagoon. I do like to show this imagery because in a simple true color composition, it shows a nice gradient of colors of the water with respect to the internal lagoon of the city of Venice, as well as of the fronting North Adriatic Sea, in which there is a nice gradient from light blue to the blue clear waters towards the pelagic areas. As said, in coincidence with hyperspectral data, Prisma collect panchromatic data at 5 meter spatial resolution. So this is a zoom closer to the city of Venice, in which with the 5 meters, a lot of application can be developed, in particular also in terms of coastal area mapping. I'm just thinking about the coastal dynamics or the delineation of the fronts. So those are also interesting data that can be merged with hyperspectral data to, in case the application needs higher spatial resolution data. So the products are provided by the agency in terms of HD5 format. The users can choose across 4 levels of products. Basically, we do have the top of atmosphere radiances, which are the level 1 products, and then a series of level 2 products, which basically all they are the bottom of atmosphere radiances. So the data are being collected for the atmospheric correction, in which also there are the ancillary products, such as the aerosol characterization and some information about the macro classes of land cover. Some other data in terms of products, all of these data have been intended to be compliant to the mission requirements at the beginning, defined at the beginning of the missions. So here we do have some of these characteristics. What is still a little bit not aligned with the requirements is the geometric localization errors, which is pretty low in performance, but that should be re-amended at the beginning of the next year. So the system can acquire every day about 220 imagery, which can be processed on a single day. And the average response time from the user order to the product ready is about 7 days. As I said, the images can be acquired worldwide, but within an illumination condition of solar zenith angle of less than 70 degrees. So to discover and access Prisma data, you simply need to compile the license form and then log into the portal, in which you do have the possibility to search for imagery data which are already stored in the catalog. So here you can browse across the worldwide to see, with respect to your area of interest, which Prisma data are available. The search can be done also with respect to temporal range criteria, cloud coverage criteria. And Prisma can also be tasked over specific area. in which the users have the possibility to task the Prisma in advance for a certain area. So this is the portal interface on how the Prisma data can be tasked. Maybe some of the acquisitions of the tasking are more successful, so there are some tip and tricks for doing that, which I recommend everyone to extend the acquisition window of the maximum, which is 1 month. So because by default this validity time range is 2 weeks. And then also ask for a contextual processing order. As default is none, but if you select at least level 1 products, you will be notified with an email from the agency that your data has been collected. So you have a quick feedback if your tasking has been successful. Then the agency has also delivered a Previsibility Tool so that in advance you may know when Prisma will pass over your study area for a certain periods. And this also can be used specifically for try to have Prisma data in coincidence to fieldworks activity or in coincidence to any other requirements of the users. So here, by having provide to the system the position of your study area, the condition of viewing and illumination angles in terms of view zenith and sun zenith, the system will provide to you the sensing opportunity of Prisma for the time window you have selected in a near future. But now after having presented Prisma, I would like now to focus more on what Prisma can do or maybe use it for aquatic ecosystem applications. As I said, Prisma is a full visible near-infrared, shortwave infrared spectrometers, which actually provide more than 200 bands from 400 nanometers up to 1500. But having said that, most of the data I will present later on are focusing on the visible to near-infrared spectrum. This is because water quality applications are mostly developed in that range. And so most of the next, I would say, all of the next slide I will present will just show the experience we had by using the data cube from the visible to the near infrared range only. So already at the time of the commissioning phase in which Prisma was not delivered to the public because was in this commissioning phase, the Italian Space Agency already investigated the potential of the sensor in investigating water targets. So those are the slides they presented during the commissioning phase, just few months, few weeks, I would say, later the launch, on the potential of Prisma in mapping bottom depth, the turbidity in a shallow lake, some properties of salty waters in a transitional system between the land and the sea, and also the plastic, those data have been collected in correspondence to the Pacific garbage patch. This is also a slide in which the Italian Space Agency tried to summarize the benefit in Prisma with specific interest on Italy. So for instance, on the top left histograms, you do see the number of lakes which can be mapped in Italy according to the dimension of the pixels. And any class of sensor between Sentinel-2 and Landsat, so in the range of 10 to 30 spatial 30 meter spatial resolution, of course, increase the number of lakes to be mapped with respect to Sentinel-3 or ocean color radiometers. But then if we are able to also combine hyperspectral data with the pan camera, of course, the number of lakes to be mapped is almost 100%. Of course, the capability of Prisma in mapping on the maps on the right, the concentration of chlorophyll is also depending on the condition of the system. Inland coastal waters are typically very heterogeneous. They may show a pretty patchy distribution of water constituents and optical properties. So that is rather obvious that by having higher spatial resolution data, you may describe better the features and the fronts of those processes happening in aquatic ecosystems. There is, of course, the advantage of having a pan camera at 5 meters just for the specific purposes of mapping. So this is the case of a aquatic vegetation island, in which, of course, 5 meters improve the mapping much better than the 30 meters. And with a specific configuration of the spectral bands on the spectra on the bottom, you can see the benefit, pretty obvious also this slide, but in which it's pretty easy to capture the features from Prisma of aquatic system, in which we do have a significant amount of phytoplankton, also some cyanobacteria, as you may see those shape here. This is due to high phytoplankton that is pretty well captured by previous hyperspectral systems, such as was Chris Probra, but that of course are totally missed from the system which do not have enough fine spatial resolutions. This is the case of MODIS, the case of Landsat, while the case of Sentinel-2 is a little bit better, at least for the bed in the red edge, to capture the higher phytoplankton peaks, and this was also the case of Meris and Olsi. But generally, having hyperspectral data is an improvement in terms, of course, of reconstructing the signal which is we can found on reflectances in aquatic system with a rather complex optical water. So the evaluation of Prisma data we performed in the last year was mostly dedicated to the evaluation of the level 1, so the top of atmosphere radiances, to see if the radiances collected at the top of the sensor were aligned to the observation performed with other sensor. And then we start to evaluate the level 2 products in terms of atmospherically corrected data, starting with those provided by the agency, even if we are aware that the correction was not totally dedicated to aquatic systems, but also testing other atmospheric correction schemes. So there is this recent paper from Federica Braga in which Acolyte is compared to the standard level 2D products. Usually those works in evaluating Prisma has been performed in coincidence with Sentinel-2 and Sentinel-3 data, because we finally think that the use of hyperspectral data has to be in cooperation with those excellent and existing missions. Those are some of the images collected by Prisma over different study sites, in particular those in which we do have IronNet ocean color systems. So here you may see a nice variation of colors across the sites. And this was the paper I was mentioning, in which we demonstrated that the top of atmosphere radiances are comparable to data collected by Sentinel-2, as well as with the simulation we did starting from in situ data with the 6S. So there is a good convergence of Prisma, Sentinel-2, and in situ data when they are simulated to the top of atmosphere over different ecosystems in coastal waters and inland. This is a basic, some graphs from the paper of Braga, in which we did the comparison of level 2D standard products in blue in both Lake Trasimeno and in a site in Venice, which the first one is a very turbid water body. The second one is a clear water from the sea. In which level 2D are plotted against the result starting from level 1 products when apply Acolyte, and in this case with Sentinel-3. All of them plotted with respect to WISP station. And the basic conclusion of this work is that at the end, level 1 data corrected, level 1 products corrected with Acolyte definitely performed better than the standard level 2D products from the agency, especially in clear waters. This was not less evident in turbid waters, even if there was an improvement. as said, this data then can be used, of course, for a very nice application. There are a lot of papers nowadays in which they are demonstrating the advantage of hyperspectral or the value added by hyperspectral with respect to the multispectral sensors. And based on literature, we tested some algorithms to demonstrate the use of Prisma for mapping water quality. Most of the examples I will provide are based on bioptical modeling, in particular the work we did in the past, in which we implemented the Zomping-Lin model developed for hyperspectral data in an IDL code for optimization procedures which simultaneously provide the concentration of water constituents and shallow water informations in terms of bathymetry and cover and type of bottoms, as well as some empirical algorithms that, of course, take advantage of having continuous bands. So you can switch across the wavelengths in order to capture the peak and the dips, depending on the concentration, for instance, of chlorophyll A or phycocyanin. By applying Bomber, so we mapped the usual parameters such as chlorophyll A and total suspended matter, along with the bottom composition of the substrates in Lake Garda. We did the mapping in this turbid lake of TSM, also with DASIS, which is an hyperspectral sensor from DLR. I'm not presenting. And also some information on wetlands in terms of concentration of chlorophyll A, phycocyanin contents, as well as information on the biomass of emerging aquatic vegetations. There was also this nice paper from Nima Palevan group in which they developed the mixer density networks for demonstrating the mapping of phycocyanin with respect to the existing algorithms such as Stefan Simis for two ecosystems, again, Lake Trasimeno, the turbid lake in Italy, and in the coastal waters in a lagoon, actually, the Curonian Lagoon, which is the largest lagoon in Europe, in which there was an improvement of the method in terms of mixed density networks with respect to existing algorithms. But again, this was performed with Prisma imagery. And we have more examples. And now I come closer to the project, which is PrimeWater, because the example I will show you later, now, starting from now, are mostly dedicated to the target areas we are investigating in PrimeWater. So they are distributed in the globe. We do have an example in a case study in the States, which is Arsha Lake, case studies in Mularja Lake, and two case studies in Australia, Hume Lake and the water treatment plant in Melbourne. So I introducing PrimeWater. PrimeWater, as said, is a H2020 project, which means it is funded by European Commission, the largest, one of the largest funding sources we do have in Europe, that aims to generate information on the effects of upstream changes on future water quality and quantity. So we do have a component of Earth observation in the system, which is integrated with additional data sources, in particular continuous in situ monitoring systems, as well as with advanced modeling, in order to do water quality and quantity forecastings. And those project is, of course, focused to the public and private sector, who has to take care of water resource management. In particular, PrimeWater is focused on water resources in which water is used for drinking water purposes. The consortium is also shown in the slide. So we do have partners from Europe, as well as the contribution from the States, from Environmental Agency, and CSIRO and SATDEC and Melbourne Water from Australia. So as I said, PrimeWater is try to improve the monitoring of freshwater reservoir and the management, in order to do also some forecasting in terms of water quality by integrating satellite remote sensing, in situ data observations, and modeling, mostly based on hydrodynamic models, which is HYPE, as well as ecological modeling, which is developed thanks to DEF3D from Deltares. So today I'm presenting the activity we are doing with respect to satellite data, in particular hyperspectral component, because in PrimeWater we do also use a lot of Landsat and Sentinel-2 data, which are not presented today. While in the next following webinars, which belongs to the PrimeWater class, there will be a webinar much more focused on modeling, so on the advantage of integrating satellite in situ data for also forecasting the quality of water in those freshwater reservoirs. As said, the study sites are distributed in Europe, in Australia, and in the States. And this is also a representation of those systems which are managed by, they are not totally naturally, because they are managed by the relative water authorities. So within the virtual lab, within PrimeWater, sorry, we established a virtual lab. This is the web address, which in general, virtual lab are online services used for a variety of purposes, education, science, research, and can be used by experts of different fields to share ideas, run experiments. And within the case of PrimeWater, this is a virtual lab specifically dedicated to research, in order to share the tools, the experience, and also providing data if they would like to test other methods or to reply the experiment by themselves. So the virtual lab so far has defined 9 experiments, which are focusing on remote sensing, process-based modeling, and data-driven modeling. As I said, I'm now talking on remote sensing, but the next seminar will provide you more information about the modeling aspect. And the experiment we defined in the virtual lab with respect to remote sensing are 2. One dealing with imaging spectrometry, and the other one with multi-scale optical data. And today I'm talking on imaging spectrometry, but every one of you is more than welcome to browse across the experiments to look how they look, do they look for. Those are the experiments most focused on modeling, especially with respect to the water quality component. And those are also experiment defined with modeling, also with respect to the dynamics and hydrodynamics features. So each of the 9 experiments has been defined in order to follow a common scheme to help us to browse across the experiment with a common approach. And those approach has been defined according to Ceola et al., in which they defined 8 stages. So for each of the experiment, we have this common template in which we do define scientific questions. We do show how to acquire and assemble in situ data, how to run the experiment, how to process the data, how to evaluate the model outputs, share results, explore the findings, and the final aim of each of the experiment is to make publication, because this project is really focusing on science. So this is how the experiment looks like. And for each of the experiment, I will browse you across how we define the people, the methodology, and the analysis of the data. So this is the first experiment on imaging spectrometry, in which we defined the title of the experiment, which is the study of primary producers with satellite imaging spectrometry. We focused most of the activity with Prisma, but also including DASIS. And so the final question was to demonstrate the mapping of primary producers in freshwater reservoirs. We hence start to evaluate the data, as I presented in the previous slides. And here is how the data are shared within the virtual lab. So for each of these, if you browse into the scientific experiment, I now stop sharing the slide just to go on the browse. in which if you do show the virtual lab here and you browse in the experiments, and we do go into the first one, which is imaging spectrometry. And here you may see all the tasks in which we have developed. We have list the participants, the methodology we apply, in particular with respect to the data preparation. We also share here some tools, such as the tool. I just want to show you how that works.
To download Prisma images, you need to log in at this site. Here you can choose between two different systems. Let's see the first one, the catalog, with all the acquired Prisma images, where you can start the research.
So here, browsing into the virtual lab, you can find some of the tools which are that we have developed for using Prisma, especially at the beginning when the mission was rather new, and which there was a lot of investigation on how to process the data, how to read the data. And for instance, with respect to the reading of the data, there is also this tool which is
So to convert them in a more usable format, you can download Prisma Read. It is a software package written in R code and it works like this. After installing the packages in the libraries,
so as I said, here you may find some of the tools we have used to make the analysis on Prisma. So I go back to the slide. I was here. So the aim of the virtual lab is also to provide such kind of information to the community. So here there was, because of course we used Prisma data in the experiment, we have to search for the data, we have to do new acquisitions. So in those videos, you may see how to search the data into the portal, as well as how to make new acquisition over the targets. We have compiled a lot of tables in which we do have the summary of Prisma data for the 4 study areas of the project. And here, again, the tools we have used, as I was showing later on, I was showing earlier, sorry. And with respect, for instance, to the work we did on level 1 products, in the virtual lab, you also find a video that shows how we simulated with the 6S code the top of atmosphere radiances to the top, to the in situ data to the top of atmosphere radiances to be compared with Prisma and Sentinel-2. So here in the virtual lab, you also find this information and the link to the R code, which provide you such kind of opportunity. So we evaluate over the study area. Basically, we are repeating in this experiment the work I presented earlier. So the evaluation of the top of atmosphere radiances, also in terms of apparent reflectances, and not only in radiances, to be at least normalizing the data with respect to the sun illumination conditions. And in this case, again, in the scientific experiment, you can find the video to convert the top of atmosphere radiances of level 1 in top of atmosphere reflectances. And with respect, instead of bottom of atmosphere products, so which means the data corrected for the atmospheric effect, again, we have evaluated, as I said, Acolyte, thanks also to the collaboration with Erbin's group. We have evaluated the level 2D products, but recently, thanks to the visit sites of a student, Tainara Lima, from the National Institute for Space Research of Brazilian, we are also, as we used 6S in the simulation, we are also using 6S to correct the data for the atmospheric effect. So Tainara is working with us for 6 months as a visiting student, and she developed this Python interface. She's running this Python interface in which 6S has been applied to Prisma data. This is an example of a study area she's studying in Brazil, in which the 6S has been applied to Prisma, and Prisma has been compared also with in situ data or with Sentinel-2 data. So this is another tool that can be used. There is a repository on GitHub for correcting Prisma images with the vector version of 6S. So thanks to Tainara. And again, of course, as we would like the scientific community to make this experiment maybe comparable and repeatable in the virtual lab, you also have the list of the products we are using and the in situ data we are using for the comparison. So those are some of the results with respect to Prisma in terms of atmospheric correction, in which standard products are compared with respect to other multispectral data or to in situ data. And basically the conclusion of this is that most of the level 2D products are not suitable for those aquatic ecosystems, even if they show a pretty nice variation in terms of peak and dips, but they may have problems, especially in the blue and the near infrared. But having said that, there is also the progresses of the state of the art. Let's talk about Acolyte. Now we have 6S, and there are other codes that could be tested and evaluated on Prisma. So I move a little bit forward, simply to show some of the mapping we have done in these study areas, mostly of them, again, made with Bomber, which is also free available and available from the code. There is also for Bomber a video which explains how to run it. And having said this, those are the maps we provided with Prisma in terms of simultaneous mapping of chlorophyll, total suspended matter, and sedum within the experiment. Other example for the water treatment plant in Melbourne. Here we use the color, so we synthesize the hyperspectral information in dominant wavelength to provide maps which are maybe more synthetic and ready to be used for different purposes. And we did this experiment on Prisma also with respect to the aquatic vegetation, in particular for mapping fractional cover, the dry weight of biomass, and the leaf area index. Sorry. To conclude, okay, we have Prisma. We will have in the future, we have Nmap. We will have in future a nice hyperspectral mission, but we do have a lot of satellites already on board, orbiting. And we do think that cooperation is a key component of using hyperspectral data. So again, in the PrimeWater, we demonstrate the use of Prisma in filling gaps, for instance, temporal gaps due to cloud cover in Lake Moularga. So this is a mapping of chlorophyll across April, as obtained from Sentinel-2 and Prisma. And this is a similar example for total suspended matter. And also here, the different acquisition times. So this is the case of Sentinel-2 with respect to DAISYs, which overpassed on the same day, but a different hour, which was able to provide data at the time when clouds have gone. So at the time of Sentinel, on 2nd of February, there were clouds on the Lake Moularga. At midday, clouds were over, and hyperspectral data provided observation in terms of chlorophyll mapping. So those are the results which my colleagues Andrea Licci also presented in the context of GeoAquaWatch. We summarize the use of Prisma in the PrimeWater project. So to conclude, again, a few words on the Earth Observation Virtual Lab, which every one of you is more than welcome to explore. This slide is intended also to provide the direct link to the tool and the results I've shown today in terms of GitHub repository or other codes. There is also the mixed density networks code, which is now under testing again from Tainara for seeing the mapping of phycocyanin with Prisma in the Brazilian case studies, and Acolyte, of course. And also we do have a partner, Iwa, in the project, who is very skilled in communication, who provide also YouTube channels on the work we are doing on hyperspectral data in the project. There are other few tools. So on the bottom, the Python 6S vector version developed thanks to the Tainara work, and also the use of the Glint tool, a work code which is available in Snap platform for the glinting. It was developed as Send-to-Coral plugin that was intended for Sentinel-2, but we also tested the glint tool in Prisma, and it also provided nice correction due to glint. There are also other sources of information prepared by the Italian Space Agency and the German Space Agency. In particular, those help you in going on with the registration for the license agreement, which can be a little bit naive, but I mean, it's mandatory to play with Prisma. And also, as we did for PrimeWater, also the Italian Space Agency provide the videos for helping you in ordering the data and to collect new data. With also some link and email if you have any technical question about Prisma. To conclude, we may say that the satellite has been successfully launched. Level 1 product seems reasonable to be used also for aquatic application. And for the level 2D products, I mean, they are not so well designed for aquatic application, but there are a lot of activities focusing on this. We already have Acolyte for Prisma, while in June this year we launched A63, so an atmospheric correction intercomparison exercise based on Prisma data, in which the state-of-the-art of atmospheric correction schemes for aquatic application will be tested on Prisma Imagery. Prisma is of course available for also testing, developing water algorithms, but there are already nice publications based on Prisma, and in blue you may see those which are focusing especially on water quality mapping. Meanwhile, we also have Nmap orbiting. I think is almost ending its commissioning phase, so soon also Nmap data can be used in synergy with Prisma and the other class of sensor for any kind of purposes. And with this one, I thank you very much for listening. Thanks.
Thank you, Claudia, for a clear webinar. I would like very much to invite now Mary Beth to take your comments and questions. This is only a start, as you have heard. There are going to be webinars to follow up on that in more details. Thank you, Claudia, for making that possible. Mary Beth?
Sure. Thank you very much, Claudia. Hope everybody can hear me.
Yes, we can hear you.
Great. We do have a couple questions, comments in the chat. First from Stephanie Scholar-Ooze. She said, very nice talk. She asks, are you using harmonized Landsat Sentinel-2? I believe it was one of your latter slides when that came up. And then she also asks what your experience, oh no, that's somebody else. So sorry. Yeah, so maybe you could, if Stephanie's still here, if we could.
Yeah, I'm here, thank you.
Yeah, maybe we can identify that slide.
Yes, I may answer rather quickly. I mean, of course, as I said, hyperspectral data has to be used with Sentinel-2 and Landsat. Sentinel-2 and Landsat are used a lot in the PrimeWater project, and we will have a deliverable to be ready next year, in which we have to show the integration across the data collected for the project. So there is the idea of using Sentinel-2 to demonstrate the synergic use of Sentinel-2, Landsat, and Prisma. By the way, there is a recent paper I have seen Milad on the call, published by Milad really today, maybe yesterday, in which we also are evaluating Sentinel-2 and Landsat 9 at that time for water quality mapping. So the work we are doing with Prisma is absolutely aligned to the progresses and the state-of-the-art of multispectral satellite sensor at the spatial resolution of 10 to 30 meters.
Thanks. Yeah, I was wondering because there's a harmonized Landsat Sentinel product, but it seemed in your images it looked like you were showing just Sentinel-2. So I was wondering, when you use both of them, are you using them individually or are you using that harmonized product?
Yes, actually, for the specific purposes of PrimeWater, the use of, in my example, there was Sentinel-2, but we are using a lot also Landsat. This is just a case. I show example with Sentinel-2, but the processing is made by operational by other partners. So there is the group of NEMA who are using the harmonized products. There is IOMA
Right.
from Germany, which also, so depending on the team, they are using both the collection or the single data as they are.
Okay, thank you.
You're welcome. Thanks to you.
So we do have another question from Tadzio. Claudia, what is your experience using Prisma to map the Benthos, specifically seagrass ecosystems?
Yes, I mean, that's good. That's good. We tested especially for seafloor mapping in coastal area in Italy, as well as in the usual Lake Garda, which is our main test area. So far, the modeling we have, it is able to map up to 3 classes of substrate. So we are still limited in mapping 3 classes of substrate, even if potentially having more bands, we may recognize much more. But then there is, of course, the problem of the inversion that maybe do not help. I think it's like to play with pretty nice data. They are not, of course, optimized with respect to the signal to noise. What we are exploring now is the integration with the PAN, so make an hyperspectral data fusions, because for mapping, we still believe that having 5 meters can provide much better information, at least for our case studies. But it's reasonable good. There is a student from Heidi Drissen who did a nice work on seagrass mapping with Prisma.
Heidi Dearson, student. Great.
Yeah.
Thank you. Okay, Gada asks, as for the modeling, which you mentioned is an upcoming PrimeWater webinar here on the GeoAquaWatch channel, October 12th. Gada asks, for modeling, I assume it is set for a specific area. Can anyone expand to other areas of interest using your technique?
Yes, the model, of course, is really site-specific because it builds not only on Earth observation data, but also on in situ data, which are available for a certain site. So you have to have at least those set of parameters. And of course, it depends on bathymetry, which is very site-specific. Then, of course, having the calibration parameters, potentially you can apply your model in any kind of, I would say, similar water resource, so similar basin in which the model can be calibrated and tested and validated, but it's quite effort. It's quite effort.
So, anybody else have any other questions for Claudia? I did just want to point out, I have promoted in the chat. If you haven't been looking there, I put the link to the PrimeWater website. It is on our page, and thankfully somebody pointed out that it had moved a little bit, so I updated that link while you were talking. And I also put in the chat the direct link to the PrimeWater virtual lab. I did have one question for you. Is there a way to, or is there a process to get, if somebody wanted to contribute, maybe one of the GeoAquaWatch working groups or something like that wanted to contribute something to the virtual laboratory experiment? Is there a process for adding content there, or is it sort of restricted?
Yes, there is. There is there is in each at the bottom of the page of each page in the virtual lab there is a contact, so a possibility to get in contact to contribute to the virtual lab. So there is this possibility, and of course there is the project website in the where do we have a lot of contacts, especially towards the project coordinator to ask for that.
Right.
And actually, I mean, and a simple email can also work fine. I mean, we are open to any kind of communication types. So there is a formal one as a part of the website, but there is also something informal that is more than welcome.
It's an excellent tool, and I think it fills a needed gap. There's lots of tutorials out there. There's lots of portals out there, but the virtual lab walks you specifically through building that skill and testing it on your own, self-paced. So I think fills a really wonderful niche. And we'd like to help sustain and contribute to that as well. Any other questions from the audience? Just unmute yourself and ask directly. Okay, you can also put it in the chat. I'm still paying attention to that. Lots of great comments for you in the chat, Claudia. So I hope
Thank
you're
you. Thank you to everyone. Yes.
taking a
So
peek
happy
there.
to receive all of this. Congrats. Thanks. Thanks for really.
So I think we'll probably end it here if there's no other questions. Thank you very much, Claudia, for your excellent presentation today, and we're happy to help support PrimeWater's efforts in the future. They're just stunning images that you shared, I think, from the Prisma capabilities, and we look forward to helping with that. Also, just want to remind everybody, October 12th is the second installment of the PrimeWater webinar, same time. And if you're not currently getting the communications from us, you can sign up for our emails on our website. The link to the website is in the chat. Just scroll down to the bottom. We try not to bug you too much, but it's a good source of information. So thanks everybody for joining us today. Congratulations, Claudia and your team, for a wonderful presentation.
Thanks to everyone, and thanks to GeoAquaWatch for doing this job. Great, thanks.
Absolutely,
Bye.
we're thrilled. Bye-bye.
Bye. Ciao.
Bye.